Today's topic is about learning from a stream of data, and particularly how we can learn a value function if we only have data. So previously, we've seen cases that we know the model, like P and R, and we wanted to find a value function for a policy or optimal value function. Yeah, so kind of we had previously the planning case, and we saw methods like value iteration, policy iteration, and linear programming. But then we actually care about reinforcement learning setting, which is when we don't have any access to this model, like we don't know P and R, but instead we only have some data. Now the question is that how we can still learn similar things like value function of a policy or optimal value function, and then eventually optimal policy using data. So what is the form of data? The form of data is in the form of stream of data. So the agent observes something like this, that a sequence of x1, a1, r1, and then x2, a2, and r2. And this is kind of generated with a process like this that at, say, time t, agent chooses action using its policy. Policy can be, of course, deterministic or stochastic, doesn't matter now. And then the agent goes to the next state according to the selected action and state that it has been, goes to xt plus 1, and then it also receives a reward, so also RT. And the question is that how we can learn. Okay, so how we can learn, say, V of P, V of pi, or V star or Q star, and then eventually pi star. And here in this lecture, kind of one assumption that you will notice is that I assume that the agent can represent these value functions exactly. So there is no approximation in representational power of agents. So the agent doesn't use any function approximator. Most of these ideas can be translated to the case that we have a function approximator, because, for example, the state space is continuous, so we can represent value function exactly. But some details can be different. For example, sometimes I have a for loop over all states, and we can't have that for loop if the state space is continuous. So let's start from a simpler problem of we have a random variable, and we want to estimate its expectation, its mean. So all of you know how to do it, but just let's go through it. So we start from the problem that we have a random variable z, and then we have, say, n IID samples from it. So z1 or z to zt. So here I guess I use t here. So t samples from it, doesn't really matter. And then the question is that how we can estimate its expectation m when z also comes from the same distribution. Okay, so I mean, this is very simple, but what is the solution? Any suggestions here or in chat? Okay, we have one answer in chat, which says that, okay, we can use mean. So yeah, we can use sample mean to take average of all of them, right? So we can essentially have something like this. So define m of t being the sample mean of all zi's divided by t. And we know that this converges to the true mean because of, say, the law of large number. So m of t converges to m in some probabilistic, in some sense, like almost surely. This quantifiers doesn't really matter, but this shows that it happens with probability 1. Always happens, essentially, and always in measure theoretic sense. Okay, so we know this thing, so that's good. But there is a problem. Suppose here if you want to naively kind of implement this algorithm, you need to record or store all your Z1 to ZT, and then compute this mean. But suppose we want to do it online in a sense that we want to have an estimate of M, like MT, but just do the updates as each sample comes without storing all of them. Because say if T is like a very large number, billions, then storing all of them would be kind of consumes a lot of memory. So what is the idea? Well, how we can do it online, do you think?
So we just keep track of the previous mean and then do this incremental process to update this mean.
Yes, that's I guess basically what we want to do, and that's how we can do it. So the naive implementation requires storing all samples. It's infeasible when T is large, but we can do it online. And I think, as you mentioned, we can do it as follows. Like how it works is that we basically want to relate MT plus 1, the new estimate, to previous estimate and the new data. So we just write it. So based on the definition, it would be samples of zi's when summation goes to T plus 1 divided by T plus 1. So I just divide the summation to two parts. One is the first part, the first T samples, summation of that. And then the second one is the new sample. This term is equal to T times M of T, which we have here. And then we have this Z T plus 1. So I do a simple algebraic manipulation. We get that we have 1 minus 1 over T plus 1 times MT plus ZT plus 1 times 1 divided by T plus 1. So this is essentially like an online update, uses the previous value and the new sample. So maybe it's good to take a kind of look at how it looks like, each of these terms. Each of these terms, this one as T goes to infinity, goes to 0, right? And this other term, as T goes to infinity, converges to 1. So this is basically saying that as we have more and more data points or observe more data points in the past, we rely more on the previous estimates more and less on the new data. Like the effect of the contribution of a new data point would be kind of diminished with something of the order of 1 over T. And when T is large, then the effect is smaller. Okay, so that's how we can do it. Let's just introduce a new notation or new symbol. And here I define alpha T to be equal to 1 over T plus 1. And then we can write the previous equation as just like 1 minus alpha T times MT times alpha T times ZT. So here the variable alpha T is learning rate or step size, and you had seen it in like machine learning courses, like when you talk about, say, stochastic gradient descent, it's a similar concept essentially. Okay, so again, with this choice of alpha, with this particular choice of alpha, the estimate MT converges to M as T grows. And this is essentially sample mean, and convergence comes from the convergence of the sample mean to the true mean. So this type of procedure, that kind of, we want to estimate something, like the mean of some random variable, but we do it online in this form that we kind of update our new value based on the previous value and some noisy version of truth that we want to find. So ZT is essentially a noisy version of the truth. this is usually, it's a kind of example of stochastic approximation type of algorithm. So this type of algorithm called stochastic approximation. Okay, any questions so far? Okay, seems to be clear. So just let's talk a little bit more about stochastic approximation and study a kind of few aspects of it in the context of estimating the sample, the mean of some random variable. So here I write the same formula as before, but I just use notation of theta instead of m, essentially to kind of distinguish it from the m, which was the sample, m of t, which was the sample average of the first m1. Why? Because here I want to change alpha from that specific schedule that we had in previous slide, 1 over t plus 1, to something other than that. So here we can choose different values of alpha. Like if we choose alpha to be 1 over t plus 1, we get the sample mean estimator. So that would be just online estimate of it. But we can think of other types of alphas. So for example, what if we choose alpha a fixed number, like 0.1, say, and then have the update, say 0.9 times theta t plus 0.9 theta t plus 0.1 z of t. So that would be the example of a fixed alpha. Or we can choose alpha to be like some constant divided to t to the power of p plus 1, or anything else, like you can think of it. These are all possible schedules, and we just want to understand its behavior. Like, does all of them work? Does all of them have this property that theta t converges to the real mean or not? Okay, so let's study the case that alpha t is constant. So the update rule would be theta t plus 1 equal to 1 minus alpha theta t plus alpha times z of t. So we can study its expectation and variance to get an idea how it behaves at the population level. So if we compute the expectation of both sides, so expectation of theta t plus 1 would be equal to expectation of the right-hand side. Then I can divide it by, it's linear, so I can divide it to two components. Here, the expectation of z of t is equal to mean, m. So the equation would be 1 minus alpha times expectation of theta t plus alpha times m. So okay, maybe I guess maybe I didn't explicitly mention here when we have some equation like this, theta t is a random variable, right? Because it's a variable that takes some random variable, does some processing on it, so it's still random variable, and randomness of it comes from zt and the previous randomness of theta t. But then if we take expectation, it is not random anymore. So expectation essentially marginalizes all the randomness. So we take expectation, we denote expectation of theta t by theta bar of t, just to simplify the notation. This is not random anymore. And then the equation that we have above would be theta bar of that time t plus 1 is 1 minus alpha theta t, theta bar of t plus alpha m. Okay, maybe before I go on, what do you think happens for the expectation, this theta bar t, when t goes to infinity? Does it converge to m or not? Okay, Okay, so one answer is converged, the other is yes, so converged, and the other depends on alpha. Okay, so I guess both of all these three answers are correct to some extent. But the answer that says depends on alpha, can you elaborate on it? Like, why does it depend on alpha? I mean, talking is faster than typing, probably. Okay, so I guess one answer is alpha depends on t. So here, but alpha, suppose alpha is constant. So I assume that alpha is not function of t. So it's like, say, just imagine alpha is equal to 1.1. The other comment is that, well, if the series doesn't have memory, it shouldn't converge to any mean, which I think I understand what it means. So for example, if alpha is, suppose alpha is equal to 1, right? Here, I guess let's choose alpha equal to 1. So what we get is theta, I mean, even from the top one, not the expectation, would become equal to 0 times theta t plus alpha times zt. Alpha is 1, so it would be zt. Okay, so in this case, if alpha equal to 1, what happens? Theta t is just, theta t plus 1 is just following the most recent sample. So it is unbiased estimator of z of random variable z, but it is not going to converge to any point. But its expectation, yes, its expectation kind of behave the same as expectation of zt, which is m. But just suppose another case, like another extreme case, is alpha is 0. Then what we have is essentially theta t plus 1 is equal to theta t. And suppose theta, we start from theta 0 equal to, say, some number 0. So this means that all theta t's at all time steps would be the same, constant equal to 0. So in that case, it doesn't converge to anything. Well, it converges to 0, but which is different from m, most likely. So we see that alpha should, I mean, so these extremes doesn't seem to be very suitable. Like 0 doesn't make sense. 1 in expectation, it's true, but it is just following the past value. But I guess there's a mention of geometric series. So that's true. I guess can be expanded as geometric series. Let's see what happens. So here I just kind of expand this theta bar. So I assume that theta 0 starts from time value of 0. So its expectation is also 0. So that's initial value. And also I assume that alpha is between 0 and 1 and is strictly smaller than 1. So I get that the theta bar of t is just alpha times m. You remember this kind of comes here. And then theta bar of 2 is 1 minus alpha times the previous value alpha m plus the new value alpha m. Theta 3 is similar, but you see that there's a pattern like 1 minus alpha squared times alpha m plus 1 minus alpha m plus alpha m. So if you just kind of write this down and in a nicer way, at time t, theta bar of t would be this summation, alpha times summation of I equal to 0 to t minus 1 of 1 minus alpha to the power of I times m, the whole thing. So if we simplify it, we get m times 1 minus alpha to the power of t. Okay, so what is the behavior of it? So if 1 minus alpha is between 0 and 1, when we make it to the power of t, it becomes smaller. So we have 1 minus something that goes to 0. So we can conclude that as t goes to infinity, this would converge to m. So what we have is essentially this, that as t goes to infinity, in expectation, our stochastic approximator converges to m. So this is okay, this is good. I mean, if it didn't converge, that would be bad, but it is not enough, because it is kind of imaginable that theta t converges an expectation, but has some large deviation around its mean, m, even asymptotically. So let's think about kind of a measure of deviation. We can compute its variance. And if we do the variation, computing the variance, we get, okay, so we get something like this. That variance of theta t plus 1 would be variance of, well, of course, the right-hand side. Then I decompose it to two parts. It would be 1 minus alpha squared variance of the random variable at time t plus alpha squared variance of random variable z. Assume that the variance of this random variable z is sigma squared, just then it is clear that this kind of based on a quick calculation, we see that variance of theta t plus 1 is upper bounded by variance of zt, which is alpha squared sigma squared. And why did we do that? So I guess, why did we get from there to here? Or how could we do it? It's simple, but just.
Because that one is a non-negative term.
Yeah, so variance is always non-negative. So it is non-negative, so we have that property. So we can show that if we do calculations similar to what I had for the mean, we get that the limit of variance as time goes to infinity converges to alpha sigma squared divided by 2 minus alpha. This form doesn't, we don't care about this form right now. What is important is here that for any constant alpha, this is not going to 0. So the variance of our estimator never gets to 0. So this is kind of different from the case of when we used sample mean, or when we chose. So in the case that alpha t was 1 over t plus 1, you recall that in that case, what we had was theta t converges to to m almost surely, which means that eventually, and one of the implications of it is that there wouldn't be any variance at the end. So it is concentrated around the mean. But the estimator that we have here, if this is the m, it gets to something like this with some variance or there, which is not going to be 0. Okay, so this is basically shows that if alpha is equal to a constant fixed number, we don't get an estimator that converges to the true value that we want. So if we want to get a convergence in a sense that is stronger than expectation, we need that alpha t to converge to 0. Anything that remains fixed does not make the variance go to 0. So one case that we have seen was 1 over t plus 1, but it's not the only acceptable one. We can think of other sequences that converges to 0 for the learning rate. But then the idea is that it shouldn't also converge too fast. If it converges too fast, then the series would not converge. Do you have an intuition or kind of example of why too fast is not suitable? Or what would be an example of too fast? I guess that's the first question.
Something very small.
Okay. Right. So I guess too fast would be like something that is very small. But maybe I make some kind of example, like sequence of alpha. Suppose it is going to be like this: 0.1, 0.1, and then 0, 0, 0, and then.
So like exponential decay, for example.
Okay, exponential decay is another good example. I think that would be too fast. That's a good example. But just think about like this simpler case. It's like 0, 0, and then after a finite number of time, it becomes 0. So it's essentially the estimator based on this only incorporates a finite number of data points. And if you have a finite number of data points, that would not be enough to ensure any kind of convergence to the true mean. Another example that you mentioned is that if it is exponential, so if it is, say, alpha t would be, so I think something like this, maybe. With some constant, yeah, I guess something like that would be also an example of this learning rate or step size going to 0 too fast. But also it shouldn't be, on the other hand, it shouldn't be too slow. So what is the right condition? The right condition is that it should satisfy these two some condition, essentially, these two summation. So what are they? The first one is that it says that if we take the summation of all alpha t's, it should diverge. So it should go to infinity. The other is, if we take summation of alpha t squared, it should converge. It should be finite. So, so these are the conditions. And let's see if what we had before, like this case, alpha t is equal proportional to 1 over t, satisfies this or not. So basically, we need to check whether I write t equal to, say, 1 to infinity. What is this one? So that's the first condition. And the other one is, okay, so what is the first summation? Or how do you compute it? Or do you recall? I guess we have, probably you have seen it in calculus. So I guess the first question is that, is it going to be infinity or a finite number, say C? So what is your bet?
I think it's going to be 2, the first one.
The first one is going to be 2? I don't think so. I think we can try it to compute it, but it wouldn't be 2. It would be 2 if you had something like, I think if you had something like 1 over 2 to the power of t, that would be 2.
Right, yeah. Sorry, I got confused.
So let's see, we have some answers. Okay. Should be theta 1 in the first line. So, okay, so t squared is greater. Okay, lots of answers. I think the comment that it is diverges to infinite is correct. So I guess someone, I think Ali mentioned it behaves like T log T or something like that. I think I'm not sure if that's the answer. The way I usually calculate it is convert it to integral and then compute the integral. So behavior of this summation is kind of approximately equal to behavior of this integral and this, okay, maybe I just upper bound b when b goes to infinity, and this is going to be ln of b, essentially, minus ln of 1. So when b goes to infinity, this also converges to infinity. I guess it goes logarithmically. So if you don't like integral, I guess you can also reason for the summation one too. And for the second one, okay, so this is going to diverge, so that's good. Oops. So, and also for the second one, you can also reason similarly that it's going to converge to some constant value. So this specific choice satisfies these conditions. Okay. So that's good because we know that 1 over t plus 1 works. So the conditions are kind of compatible with what we had seen before. But then you can try, I guess, different cases, and it might be fun experiment or exercise to see which series conversion, which series satisfies these equations or not. So I think this example probably doesn't satisfy because the first one would not diverge. It would be finite number, and the second one as well. Okay, so any questions so far? Let's do some polling. Okay, let's see how is the pace. It's too slow, too fast, or just right? Almost 72%. Okay, there are a few people who are not by the computer, probably. Okay, I think that's good enough, similar to, I guess, before. I think we had too fast before, not this time. Too slow, like 11%, 89%, just right. I mean, the sample size is smaller this time, so I think the number of students now is less than the first session, but I guess that's reasonable. Okay, so that's great. So this is for just single random variable. Assume that now we want to go talk about learning the reward function. And recall from, I think, the first lecture that we had this immediate reward problem that was like we had this agent interacting with the environment for only one time step, and then the episode ends, and then it restarts a new episode. So the setting, just as a reminder, was like this. So at episode t, the agent starts at some random state xt coming from some distribution, chooses action at, and then it receives a reward rt, which depends on xt and selected action at. And then the agent starts a new episode, independently selected, again from the same distribution row. So that would be episode t plus 1. And this process repeats. And the goal was to act optimally, like choosing how to choose A's in order to get the most reward as possible. And if you recall, if you recall, we were talking about like expected rewards. So essentially the optimal policy in that case was that if we know reward function, then for any state X that the agent is, it should choose the one with maximum action. So it takes a maximizer over actions, and that would be the optimal policy for it. I think I had a question here. Okay, so there's a comment that this is contextual bandit. Yes, I guess you can think of it as a contextual bandit problem. That's right. But we haven't really talked about bandits yet, but that is an example. Okay, so if we do not know the reward, what should we do? So if we know the reward, the solution is easy. If we don't know the reward, what can we do? Okay, so what are suggestions?
Calculate the advantages of each action.
Like estimate the advantages?
Yes, estimate using state action value function and state value function.
Okay, and how do we estimate that? Like if we don't know the
so basically, so basically for each action, you can calculate the difference between the Q function and the B function. And then you select the action that maximizes this difference.
Okay, that's fine, but how do you compute Q?
Q learning.
Okay, so that's, I mean, it's a kind of a few steps ahead. Based on, I guess the answer I'm thinking of is based on what we learned, like this stochastic approximation and computing the sample mean of a random variable. I just want to extend from the case of one random variable, Z, to the case that we have a reward, or reward distribution. Let's see if we have other answers. Okay, so I guess one answer is perform many episodes and estimate the reward. And the other is take the mean. And I imagine by take the mean, it basically means that similar as the other suggestion, like perform many episodes, estimate the mean. Okay. Again, another suggestion is act randomly, track statistics, and act on those. The other is that treat each R of T of X and T as a random variable estimate. So I guess these are all good points, and all of them are, some modifications are right, I mean, if you make them complete description. So just let's start from, I think, this idea that let's just treat each of random variables R of X and T as a random variable. Like for each X and A, we have this reward distribution. And if we get a random variable sampled from it, this is like exactly this one. So this is like a equivalent of what we had in several slides ago, like each of Z's. So each of R acts like each of Z's, but instead of having one random variable, we have many, one for each pair of state and action. And just we can use whatever method we have, stochastic approximation, or use sample mean to estimate it. So the idea is that, okay, use stochastic approximation, for example, to estimate R of X and A. So it's a kind of extension of how we estimated the mean of a single random variable, Z, to many random variables, each of them indexed by X and A. So let's denote, instead of theta T, we denote, or we define R hat of T, which is kind of a function that maps from state and action to a real value. And it would be our estimate of R at time T. Okay, so that would be the process. And the idea is that eventually we want to have some R of T that would be the same as R for all state and action pairs in the state space. Okay, so that's the basic idea. Let's denote a state action indexed sequence alpha t at x and a as the step size for x and a. So this is this might look confusing, but it is not. It is essentially I'm defining one step size for each x and a. Previously, we only had one random variable. So we had one sequence of step size, alpha t. Here I have the same thing, alpha t, but one for each x and a. Okay, and then how can we update it? So I can use the same update as before that I denoted by theta t plus 1 is equal to 1 minus alpha theta t plus alpha t of z of t, the observation. Here we get something similar. So it would be when I observe xt and at, we update the random variable or estimate of r by just updating the one at xt, the value of it at xt at, with this update rule, that it would be 1 minus the learning rate there at that state plus the times the previous value times the learning rate times r of t, and r of t was from that specific x and a. And so I only update it for the state action that I have observed, and I keep the previous one the same. So our estimate of r hat t at t plus 1 at state x and a when x, okay, from when x and a is different from xt and at, I keep this previous value. So here, I guess what is maybe one way to think about what is happening is that I use t as a kind of global time step, but for each of those points, x and a's, they have a local clock in some sense. And the local clock of it would be that whenever they are selected. And it might be the case that they are not selected, but for sure they would not be selected as often as any x and a. Like we have states, say, state 1, we have 100 states, and each of them, suppose we have 2 actions. At time 1, I select state 50, and action 1, I update all the value of all others by just copying the previous value. And the value of the current, the 51 and action 1, I update it using the rule that I have here. Okay, so this is essentially the same as before. We need to have some stochastic approximation conditions as before. The difference is that now the learning rate, the condition should be satisfied for each of x and a's. So for each x and a, the summation of alpha t should diverge, and for each, the squared value of it should converge. So that's the kind of condition. Maybe one note here is that when I'm not updating it, you can think of it as having learning rate that is equal to 0. So for, maybe I write it here, for x, for x and a that is different than xt and at, it is as if I'm updating it with 0 times r hat of t and x and a plus 0 times, we don't have any rt, but just we can think of it 0 times 0. So here, the learning rate as a function of t at that time step is equal to 0 for those state action pairs that are not selected. So when we want to interpret these two conditions, we should see that for those time steps that we haven't updated them, alpha t for those would be 0. Is it clear? So here, I guess the idea is just for all the values that I update for one particular x and a, the summation of the learning rate that was effective at that point should diverge.
One question. Why do you have x here? I mean, you could have like, what's the point of having x here?
Okay, so because x here, you mean in alphas or x in R?
No, I mean in the problem setting. Like, it's kind of irrelevant of x, right? It's just, if you solve for one x, it's actually solved for all x because they're just random parallel questions.
No, well, if I guess the way I started in the first lecture was saying that this is similar to the problem of, say, full RL problem or planning problem, that the time step or the horizon is equal to 1. And then we can extend it from 1 to 2, 3, or t in general. So that's why I used kind of as a special case of a full RL problem.
I understand.
With 1 step time horizon.
Yes.
But you're right. I mean, I could also define it as just R of A without talking about X. And I think, as you mentioned earlier, consider it a bandit problem instead of contextual bandit problem.
Yeah.
But I thought that this would be a kind of close, nicer transition to the full RL problem. Okay, so yeah, let's try to finish this part. So the question is that how should we choose alpha t? The idea is that we can do it as before. We essentially need to define it to be a sequence with those properties. One way to define it is based on kind of this following way, that we use a counter on how many times x and a has been picked up at up to time t. So n of t, I define it. So maybe I have it as a kind of definition. For state x and a would be with index t would be number of times that xiai is equal to x and a from time 1 to t. So it just counts the number of times that this is satisfied. And this is kind of like counting the site of that set. And then if I do it, then I can choose alpha t for state x and a to be the number of times that it has been selected. And if I do this, then R hat of txa would be a sample mean estimator of all the rewards encountered at state x and a. Okay, is this clear so far? Okay, so now the question is that what happens if I don't observe some of the stated actions? So for example, if the sampling distribution x of rho never chooses some particular state x0. So that's one possibility. Another possibility is that suppose the policy pi for some state x0 never chooses a particular action at that state x0. So what happens to our estimates? Any guess? Okay, so maybe we can have a quick break here. Now it's like 2. Maybe we can start at 2:05 in five minutes. Okay, so what happens if, so for example, the sampling distribution doesn't choose some particular state? or the policy doesn't choose some particular action. So I try to give a kind of quick answer now, but then we go in a few slides, we talk about it a bit more. Now, the short answer is that if we don't have sample from some particular state, then we won't have any good estimate of that reward function at that state. The requirement here is that we essentially repeatedly choose some states in order to converge the true value of it. But if we don't repeatedly choose some state or state action pair, we can't have a very kind of good estimator of that reward.
Can I ask something?
Sure, yeah.
Couldn't we end up reaching state x0 through other states?
Here the assumption is that it's kind of like the length of episode is only one. So we select state, choose action, and then kind of the trajectory doesn't continue.
I see. Okay.
So it's kind of like this part of it, that the agent then restarts from a new independent episode, and then at that state it chooses again from R xt from rho. But you're right that in the case of like reinforcement learning, in general, if it's a multi-step problem, the capital T is larger than 1, it is possible that we start from this state but reach another state. So even though we never start from this state, we might have sample from there. Okay, so now let's talk about how we can choose actions, because that was the initial goal, like how to find a policy for this simple problem so that we get a good performance. And previously, what we did is that we were saying that if we know the reward function, we compute the argmax of it, and that action would be a good action. So maybe A star, the optimal action, would be pi of G. Okay, here we don't have R, but we have defined a procedure for estimating R by R hat of T. So we can compute the greedy action using R hat of T. Okay. But there's a problem. So this greedy pulse selection, if R hat is an inaccurate estimation of R, then the agent may choose a suboptimal action. And kind of the worst part is that, well, choosing some suboptimal action occasionally is okay. But the problematic situation is that it is possible to get stuck in choosing an action that is suboptimal forever without any chance to improve its estimate. And this is not okay or desirable. So when does this happen? I give you a kind of simple example. Suppose we have a problem that when we have like one state with two actions A1 and A2, and then the reward functions at that state is defined like this. For action A1, we get reward 1, so a positive reward. At action A2, we get reward 2. So choosing action A2 is preferable to action A1. And suppose the reward is deterministic. So there is the reward distribution always returns 1 or 2 depending on the choice of action. And then suppose that the initial estimate of reward, R hat, at state x1 is equal to 0 for both states, for both actions. Is it clear, this setup? Okay. Suppose that at the first episode, T1, the agent happens to choose A1 by chance. So how would the estimate would be? Like, we use stochastic approximation to update it. So R hat 2 of state action 1 would be 1 minus alpha 1 times 0, previous value, plus alpha 1 times 1. So this is going to be a positive number. But what about action 2? For action 2, we don't change the value. So we basically copy the value of r hat 1 to r hat 2. And the value was 0, so the value would stay 0. Okay, now the next time, in the future, agent comes to state x1 again, and then it follows the greedy policy. What is the greedy policy selecting here? The one with the higher, so the greedy policy selects based on r hat at some time t. R hat for action 1 has a larger value based on this estimate. So the selected action would be A1 again. And then, so this is next time step for R hat at the new time step for A1 remains positive. But A2 is not selected, so the value stays the same as before, so it would be 0. And then as long as the agent follows the greedy policy, it always chooses action A1 and never chooses action A2. So gradually, its estimate for the reward of action 1 at that state converges to the true value of it. So that's good. For one of the actions, the value converges correctly. But then for the other action, it stays 0. So then the estimates, R hat, okay, becomes more accurate, but then R hat 2 of action A2, sorry, this is going to be R hat T at action 2 remains inaccurate. Okay, this is problematic because the optimal action is actually action A2. But just by chance, because we started from choosing action A1, we state the greedy policy kept choosing that action instead of the right action. Okay, is this clear? So what can we do now? Like, how can we address this issue? So just give as many solutions as you can think of. Okay, so one answer is epsilon greedy. The other answer is occasionally choose the other policy at random. So I think it means other action at random. And I guess the other is that don't always choose the greedy policy. So these are all good. Like this is the right way to address it, the right idea. That maybe it's good to think about why greedy policy is failing. Like if we knew the actual value of R, greedy policy was the optimal policy, right? From here, if we know the actual R, the greedy policy chooses the optimal action. But then if it is not, okay, there is another comment, let's see. Okay, so that's a good point, I get to that. So if the greedy policy starts from the true value, then that would be optimal policy. But if we start from a kind of wrong idea, like estimate which has some error, the greedy policy prevents the agent from choosing other actions, and as a result, kind of gaining information about the other possibilities that the agent has. I get back to that comment, but one solution here is that, as you mentioned, a few of you mentioned, we can use epsilon greedy. The basic idea is that force the agent to regularly pick actions other than the ones suggested by the greedy policy. Epsilon greedy is one way to do it. So epsilon greedy is defined as pi of epsilon. So for some positive epsilon, and given input r hats with probability 1 minus epsilon. We choose the greedy policy, and we are at state x, so that would be the selected action. But with some probability epsilon, we choose a uniform action. Maybe I change the name here. Uniform action from all the possible actions that we have. And epsilon is usually a kind of small number. I mean, we can have a schedule for it, but say we can think of it as 0.1. And so with 10% probability, we choose a random action. With 90%, we follow greedy. So the thing that happens here is that uniform choice of action in the epsilon greedy helps us, or helps the agent to explore all possible actions, even if the action doesn't seem to be optimal, even if it chooses even suboptimal actions. The other one is that the greedy part of it, it's based on the current knowledge of the problem, which is encoded here by r hats. It tries to exploit that knowledge and maximize the reward, given that knowledge. But of course, because that knowledge might have some inaccuracy, exploiting it all the time is not a good idea. So this brings us to this question, this trade-off, famous trade-off in our reinforcement learning, called exploration exploitation trade-off. So we want to exploit our knowledge if the knowledge is accurate. If the knowledge is completely accurate, then we should always exploit that knowledge. But when we have some kind of uncertainty about the world, then we should not be very overconfident about our knowledge and exploit it all the time, because we may miss other possibilities, other actions. So it is better to occasionally choose, say, other actions in this case, in order to increase our knowledge. And then the trade-off between, like, how we should trade these things, like how balance these things, how often we should exploit and how often we should explore, that's a kind of very interesting question and a kind of active area of research. Epsilon greedy is just a solution for doing so, which is a kind of like heuristic, but it's not necessarily the best way. To begin with, you can ask the question of how to choose what epsilon is the right value. Should I choose it equal to be 0.1 or 0.2? Maybe even I should change epsilon depending on how much knowledge I have gathered. Like in the beginning of learning, like when t is small, the number of episodes so far is small, I probably need to explore more, choose other actions, because my estimate of actions would be not very accurate. But when t is like million, after a million steps, probably I don't need to explore 50% or 20% of time, maybe just 1% of time. So that's a exploration exploitation, and why epsilon greedy kind of balancing it. Another heuristic is called Boltzmann distribution, or softmax, or Gibbs distribution. So the idea here is that we select an action according to the Boltzmann distribution. So what's Boltzmann distribution? So given a parameter t, tau, and a reward function r hat, then the probability of selecting action A at state x is like this. That's the probability of choosing action A, so this is going to be stochastic policy, would be exponential of r hat of A divided by tau, divided, the whole thing divided by the summation of all A primes of this exponential of A primes. So this denominator is just a normalizer. So here, this exponential essentially says what is the weight, or what's the probability of each action. So let's kind of study its behavior. If, as a function of tau, and consider two extremes. One extreme is that when tau goes to infinity, and the other extreme is when tau goes to 0. So when tau is going to infinity, I guess you should argue or think a little bit about it if you haven't seen something like this before, that the behavior of this distribution would be similar or would be exactly the same as the greedy policy. So it always chooses action that has the highest value of R. And if tau is becoming 0, the effect of all actions, or the probability of selecting all actions, becomes the same. So the distribution becomes close to uniform distribution. So by changing this tau, we can go from exploiting greedy policy to completely exploring uniform distribution. So tau parameter is kind of a way that we can change this behavior, somehow similar to, but the similar idea than as in epsilon of the epsilon greedy, with the difference that epsilon of epsilon greedy always either choose the best one, or for the rest, it gives the same chance, the same probability. Here, the probability depends on the value of R hat. And in general, if the R hat for some action is higher, the probability of choosing that action would be higher. How much higher depends on tau. Okay, any question? Okay, so there is one question. Okay, so what about smoothing? Can you explain more? What do you mean by smoothing here?
So it is like we have missing entries and, well, yeah, kind of like the data is imbalanced. And
you mean
yeah.
For actions, you mean?
No, I mean the reward.
Okay,
the
right.
Reward distribution, yeah.
So what would be the missing reward here?
So the state action pairs we haven't explored in the samples.
Okay, and then you want to kind of smooth it like based on the previous value. So for example, if you know that reward for action 1 is, say, okay, so I try to draw what I think. So this is action space and this is RR, you know, for action 1, 2, and 3. So you know action 1, the reward has this value. For action 2, the reward is this value, but we don't have any samples here. So are you saying that we kind of maybe say that that would be our guess?
Yeah, that's what was my original thinking, but not necessarily logical, I guess.
Okay, so, well, I want to say, well, if we have a discrete action space, there is no neighborhood structure, non-trivial neighborhood structure between them. So 2 is not necessarily between 1 and 3 in some sense, because I could call them essentially they're A1, A2, A3. A1 may be choosing apple, A2 may be choosing car, A3 choosing banana. So you can say that the value of A2 is something between the reward of A1 and A3. But if we have a continuous action space, then we have some kind of nicer kind of topological structure there. So a number that is between 2 other numbers, probably we can expect the value with some assumption on like smoothness to be between those others. Like if we assume that, say, the reward function is something like this with some smoothness property, even if I don't know the value of some points, I can try to infer it from others, the neighborhoods. And this is, you can interpret it as what essentially function approximation is trying to do. It tries to interpolate from the values that we had seen for the points that we haven't seen. So your suggestion, smoothing, kind of makes sense if it's continuous action space, but for discrete action space, maybe not.
Yeah, I'm not saying that we should hold the assumption that A2 is not necessarily has the reward that is between A1 and A3. For example, if we do a softmax using exponential, we can add a small delta to each term and then calculate something like that.
Oh, okay. Okay. So here, okay. So in this softmax one, okay. So here, if softmax, even if we start from r hat equal to 0, that is still behaves like epsilon, adding epsilon, because the probability would not be 0. So the probability would be exponential of 0 divided by something. But exponential of 0 is not 0, it's a positive number. So still, even if we believe that reward is, we don't have any prior knowledge, we set it equal to 0, there's a positive probability of choosing that action using this Boltzmann formulation.
Yeah, thanks.
Okay, so let's go faster. Okay, so we studied single variable. We considered the case that the time horizon is equal to 1, so immediate reward problem. Now let's think about the general RL setting, continuing task type of things, maybe, that the length of episode can be more than 1 or maybe even infinity. And now we want to estimate the value function. Right, okay, so I actually forgot something. One of the comments was, I think Farahmand, that says, Farahmand mentioned that how to, a few slides ago. Okay, so I guess how we can deal with this problem. How we can deal with it, what the idea that I explained was based on adding some noise. But there is also comment that maybe we can start from higher starting value. Do you want to talk about it?
Okay. If we start from a higher value from all of them, then the thing is that even if we start from a wronger, like A, if we choose a wrong A action, then the estimation will just decrease.
Yes.
So yeah. So
yeah,
it will be less preferred.
So this idea is, yeah, so this idea is essentially saying that it's called optimistic initialization. So here the problem that you see here started because the initial value of r hat was equal to 0, but the true value was 2. So if we started from a larger value that is larger than all of them, like suppose we started from r hat for all action equal to 10, say, then this wouldn't happen here. Instead of, if we select action 1, so this becomes something like 1 minus alpha 1 times 10 plus alpha times 1. But this one stays equal to 10. I don't know if you can see it here. It becomes a bit. So it becomes 10. So the next time step, actually the agent chooses action 2 instead of action 1. So here, what happens is that the agent starts from an overestimate of the values and gradually decrease them. And as long as we are higher than the actual value, the agent keeps selecting that. So either we are overestimating it and the agent chooses it, or we already converge to true value and then the agent doesn't choose it. So this would address this problem, so optimistic initialization. And that would be kind of one way to think about this problem. But I guess generally it's not, well, I think it wouldn't be a very systematic way to ensure exploration and balancing them. So there are more recent I guess other comments, Brian mentioned that upper confidence bound. So there is another type of algorithm called upper confidence bound, or UCB, which is a kind of more systematic way to deal with this exploration exploitation trade-off. Epsilon Greedy is a heuristic, but if you want to do it in kind of more principled way, this UCB type of algorithm does it much better. Like so asymptotically, it's optimal. In some sense, that should be defined. I think I'm going to talk about it, not now, maybe in another lecture on bandit problems if we have time. I kind of have one lectures on these type of algorithms, or at least I try. That's a plan. Okay, let's get back to this problem. We want to do policy evaluation. So we want to learn V pi or Q pi of a policy. So in previous lecture, I mentioned that policy evaluation problem is a problem of estimating the value function of a policy. Eventually, we want to find the optimal policy, but doing policy evaluation, finding V pi and Q pi is going to be useful because as an intermediate step of many algorithms, like policy iteration, if you recall, it had a policy evaluation part and then policy improvement part. So if we can do policy evaluation, that's kind of solving half of the problem. So let's talk about policy evaluation, and then I later get to the control problem, which is finding, say, Q star and pi star. So here we don't know the model, so what can we do? The idea is to do the same as before, as what we did for estimating, say, the mean of a random variable or the reward, but just with a different random variable that you will see is going to be the return. So what is the idea? Here, okay, recall that value function, we have seen it several times already. Value function is the expected return or conditional expectation of return when the agent starts at state X. So G of pi at T is essentially the return from time step T onwards to the future. So maybe just, if this is kind of agent's trajectory at time 1, 2, 3, 4, so this would be G pi, the reward that it gets from here to the end, that would be G1, let's say another color for, okay, then maybe so this one would be G1 pi, and then the return that it gets from time step 2 would be G pi 2, and so on and so forth. So that's the kind of this notation. So what was important, or kind of nice property of it, is that, well, this is a random variable. G pi is a random variable with expectation that is equal to value function of pi. So if I want to estimate the value function of pi, I can just use G pi at that state as an unbiased estimate of that value function. So if the agent starts on state X, follows policy pi, then we can draw one sample of random variable G pi by just computing the rewards that the agent gets through the trajectory, through the episode, and then we add them, and that would be on one unbiased estimate of value function. And we can do this process for many times. Like if I start from that state, maybe I use different color, start from the same state, but oh, that's interesting. In another simulation, you can think of it. The time, so this was 1, 2, 3. So this would be 2, 3, 4, but in a different trajectory. So I can get another estimate by following this trajectory. Maybe I use an index I here to say that these different trajectories. And then I can compute the sample mean of them. And this, if I do it many times, sample mean converges to true value, which would be true expectation, which would be the value function. So here I have a procedure for estimating the value function by just running these trajectories until the end of episode or forever for continual task. And that gives me an estimate. So I guess one thing I want to mention is that sometimes each of these trajectories, so this procedure is called Monte Carlo estimation for policy evaluation for that point. Like it's a Monte Carlo estimate of value function at state X. And each of these Monte Carlo trajectories are sometimes called rollouts. So we are rolling out. So that if you read somewhere or if I mention that we have several rollouts from one state, it means each of these trajectories here. Okay, is this clear or do you have any question? Okay, that's good. So if we repeat this process from the same state many times, we get some g pi of 1 at state X, g pi of 2 at state X till n. Okay, so maybe I use t. And then I can compute the sample average, and that would be the estimate that then converges as t goes through infinity to v pi of x. Also, we can have a stochastic approximation procedure. Instead of collecting all those data points, we can do it online. So if we do it, the process would be like this. So this is Monte Carlo estimation for policy evaluation problem. And this variance is called sometimes initial state only variant. You will see why. So, okay, so how does it start? We start from some value function v hat of pi, set it arbitrary, like equal to 0. And then for each episode t, we initialize the initial state x1 according to some distribution, like randomly choose one state. And then we follow policy pi to obtain a sequence of state action reward until the end of the episode. And then we can compute G1 of the return for from the time step 1 as usual. So I just add the cumulative sum of the rewards. And then after it's computed, I do a stochastic approximation estimate of it. So v hat of t plus 1 at state x1 is 1 minus learning rates times the previous value. So this is time at time t times learning rate times the return at that episode. And then I go again, initialize a new point, and then process, keep updating v hats of pi. Okay, so any question?
Is the last line, is that overriding the previous value, or is that a like kind of like a new value?
So this is going to be the new value, like index t plus 1. And I use the previous value to get the 1. This is going to be only for the state that is updated. For the state that is not updated, I basically copy the previous value.
Okay, so you kind of like once you update this, you don't really need the previous value anymore, right?
Yeah, exactly.
Yeah. Okay.
I could write all of these things without having even index of t, and just with understanding that I take that value, overwrite on the previous value. But here, by adding t, I guess the benefit of it is that it shows like what is the global time step.
Yeah. Awesome. Thank you.
Sorry, I think in line number 7, I think the reward, the subscript should be k.
Right. That's right. So here, this should be k. That's a good point. Thank you. Yeah, so sometimes you change this index, it gets confusing. So yes, that's k. Thanks. Okay, so this previous procedure might be a bit wasteful of our data. I guess my question is that why? And then I guess the second question is that how we can improve it. So why is this procedure wasteful?
Because we are assuming the memory list Markov properties. There are a lot of redundant states that can be.
Okay, so there are a lot of redundant states. Can you explain a bit more?
By redundant, I mean for the same states, they should have the same value on average.
Okay, I see. Yes, okay, so I guess that's a good point. Like we have this kind of structural properties in MDP that says that the same state, the value should be the same, but this procedure is not benefiting from it. This procedure essentially does not benefit anything from the Markov process or Markov this MDP. It works even if it is not MDP, which can be advantage or disadvantage. But I'm thinking of another idea. Okay, so I guess these are good points. Like one answer is that because we always run it for the whole episode. Okay, so what else could we do? So I guess maybe I read the other answer. Okay, so TD learning, yes, that's I guess what you basically mentioned already or alluded to. So the other answer is that you only update the first state. And I guess the other is that we can update for each of x, a, x prime a, which I think is the same. And the other is that have g of k for all k's larger than 1. So here, I guess the idea is that instead of just using g of 1, we can use g of, okay, I use some other index, say I, for I larger than. I could update it for all those states. So here, in previous slide, here, essentially what we are doing in this procedure, we are only updating the value at this point, at the beginning of the episode. But then we also have the value of, say, this for the orange one. We also have the value at the second time step. And we also have the value of the third time step by just counting the reward that we get from second time step onto the end of the episode. So we are throwing all those data away, and we are only updating or in the procedure I described, we are only updating the first time step. But we could do it for other time steps too along the trajectory. So that is why this procedure that I described is called initial state only. At the top, you see the name is initial state only. But we could also sample or keep updating for the rest of the trajectory. So you will see that, so you can think of it, there are two variants of it. One is first visit, the other is every visit. The detail is not super important, but the basic idea of both of them is that use all the returns that we get in all time steps to update it. There is some subtle difference between them. The first visit updated only the first time that we get to that state. And if we get to that state second time, it doesn't update. Okay, so maybe I try to draw it. And then we get here. So the first visit one, okay, this state is okay. This state, okay, so we have a say, return of G1. So, okay, this is 1, 2, 3, 4, 5 again, 6, 7. In the first visit, in one variant, okay, for each of them, we can define G of 2, then G of 3, G of 4, G of 5. And you see that G of 2 and G of 5 kind of gets to the same states. So in one variant, we use both G of 2 and G of 5 in order to update state 2. And the other variants, we only use G of 2 to update state of 2. The second time or third time or kth time that we get to that state, we don't use that information for updating it. So the first variant is first visit. The second variant is every visit. The reason that the theory of these things is a bit more complicated. The problem with every visit is that, I mean, it sounds maybe potentially more efficient, but the data points that we get would be, in some cases, it can be dependent. So like G2 and G5 would be dependent random variable. They're not IID anymore. So that causes some problems. And even they can be biased. They wouldn't be unbiased estimating some problems. And then in order to avoid this unbiasedness, we may kind of avoid using G5. One comment is that if your state space is very large, like to compute these returns, I mean, you can do this procedure for a very large state space, a continuous state space. Representing the value function is problematic there, but computing the returns is easy. Doesn't matter if it's continuous or finite MDP. In larger state space, the probability that you get back to the same state would be, in some situations, would be 0. You never get back to the exact same real valued number, unless the system has some special dynamics. Like if you have a kind of contact point, like it has a kind of hybrid dynamical system, you have a contact point, like if there's a robot that jumps up and down, whenever it jumps down, gets to the surface, even though before that point, the value of, say, the robot, the point, kind of the body of the robot is a real value, so never get to the exactly same point. But whenever you contact the surface, that point would be exactly the same, assuming the surface is solid. So in that situations, even in continuous state problem, we may get back to the same state more than once. But in general, if we have some nice properties, we never get back to the same state again. So in that case, first visit and every visit Monte Carlo estimates, both of them would be kind of the same in some. Okay, so this is kind of like a big digression. So this is Monte Carlo estimator. Let's try to talk about temporal difference learning for policy evaluation. So some of you have already mentioned as a probably more efficient way to do it. So what is the idea here? The general idea is to benefit from structure of the MDP in order to have a probably better estimate of value function. So how does it work? So the Monte Carlo estimate allows us to estimate V pi by using returns. It does not benefit from the recursive property of the value function, which is encoded in the Boltzmann equation. So we know that some value of some states are exactly the same. If you return to the same state, the value of it is the same. Or there is this special structure encoded by the Boltzmann equation. But Monte Carlo estimate does not benefit from it. So in fact, MC is agnostic to the MDP structure, which may be good or bad. It is a good thing if the problem is not actually an MDP. Like if the underlying problem is not MDP, which means that it doesn't have that Markov properties, MC might be actually be a good solution. But in this course, at least for most of it, we assume that the problem is MDP. And in that case, MC is not taking advantage of that property. So if the problem is MDP, then it is not benefiting from it. Okay, so in previous lecture, on when we talked about, say, value iteration, policy iteration, we've seen methods that could benefit from the structure of MDP in order to find, say, value function. Here, the idea is that what those methods required us to know reward and transition dynamics P. What can we do if we don't know them? Here, the idea is that to have method like that, but we just data. Okay, so there's a question. Okay, so question is that if the problem is not MDP, why do you call it RL? So the reason is that, well, the problem is still RL, but, or maybe better to say like this. The problem of RL is, the way I define it, is very general. It's like we have an agent interacting with some environment, but then we have some assumptions, some special cases that can be formulated with the mathematical formalism of Markov decision processes. But the problem itself is RL, whether or not for this specific problem, the MDP framework applies or not. So for example, we have something called like partial observable MDP. It's a kind of more general framework than MDP. The problem is still RL problem, even though the methods, MDP methods, cannot work or should be modified in order to work. But the way I see it, RL problem is kind of very general, like agent interacting with the environment. Then for the solution method, we can stick to some specific assumptions. Okay, so that's, I think I will be over time for several minutes, but I like to finish this lecture. Okay, so this idea is temporal difference learning for policy evaluation. It's not clear what temporal difference means here, but it will become clear soon. So let's think about policy value iteration problem for doing policy evaluation. So value iteration for policy evaluation, how do we do it? At state X, the procedure is computing, updating V of k plus 1 at state X to be reward or pi at X plus gamma times the value at the V of k at the next state. So we have seen it several times. If we know R and P, the problem can be computed easily if we can compute the integral. But if we don't know, what can we do? So let's think about this problem, but in a kind of sample-based version. Like how we want to convert to a sample-based version and then solve it that way. So what is the idea? Suppose that we have samples in the form of AI selecting policy, or at state X. Okay, so suppose we're at state X. According to policy, we choose AI, and then according to state X and AI, using P, we go to X prime I, and then also we get a reward, which should be This is reward, this kernel. So also we get a reward depending on the reward distribution, condition on X and AI. So we can define these things. Now define, using these samples from these random variables and VK, we can compute yi equal to Ri plus gamma times Vk of xi prime. Let's look at each of these terms separately. So if we compute the conditional value of this random variable Ri, condition on X, it would be exactly R pi of X. Because R pi of X was defined as the expected value of that reward condition on choosing, being at state X and choosing actions according to policy. For the second term, if I compute the conditional expectation, so conditional expectation of Vk at xi prime of xi prime, condition on x being x, small x, would be essentially this distribution. So it would be P of the x prime condition on x and a, or this integral, sorry, not distribution, times pi of action condition x times Vk of x prime. Okay, so you see that this point, this part is exactly the same as what we have here in the definition of the Bellman operator, well, applying the Bellman operator to it. And also the reward part is exactly this one. Okay, so what does it mean? Maybe I just get my headphone. Okay, okay, can you hear me? Okay, perfect. And hopefully I will hear you too. Yeah, sorry, there's noise construction, but I can't do much about it.
Okay, so I think, okay, I guess you are hearing it now from the headsets. Okay, so any idea, like what does this mean? Like we have yi, and each of these components, expectation of them, conditional expectation of them would match these terms that we had in the true Bellman value iteration. Does it suggest any methods? Let's see if there is any answer. Okay, so maybe I go one step more. Okay, there is an answer. Okay, mean squared error, defining that. So, okay, I think that can be connected, and probably I'm going to talk about it later. But just before that, yeah, I guess we can use mean squared error for estimating something, the value function. And that's a good point, but even more basic than that. The point here is that the conditional expectation of yi, condition on x, which is this one, is exactly equal to t pi applied to Vk and evaluated at state x. So this means that yi is an unbiased sample from the effect of t pi on Vk evaluated at x. So this is means that we have something like in value iteration, in order to do value iteration properly, I need to be able to compute this integral. But if I don't know the model, I can't do that computation. But if I only have samples from that model, except these samples, without knowing that P and R, just samples, random variable sample from that, the conditional expectation of those random variables kind of combined in this way would be the same as what I wanted without actually knowing the Bellman operator and the model. Or another way to think about it is that I have a noisy version of it, a noisy version of this Bellman operator applied at X. So I can use a sample mean estimator to estimate this, or I can do, as you've seen a few times already, we can use the Bellman as stochastic approximation. Okay, so let's define a new notation. So I call it the empirical Bellman operator. So T hat pi of Vk, so there's a T hat here, would be the reward that we get at state X plus gamma times Vk times X prime at X. And here by X prime at X, I mean X prime that is generated by starting from X and having one sample from distribution, the transition dynamics. Okay, and then this quantity is essentially Y that I had in the previous slide. So I just have a different notation here. The conditional expectation of it would be T pi of Vk at state X. We can think of empirical version of value iteration now. So value iteration was, say, Vk plus 1 was T pi Vk. So that was the usual value iteration, but just imagine that I do it this way. So we have T hat pi of Vk, and this is for just studying what happens. So I can decompose it to two parts. The part that is T pi Vk plus the part that is T hat pi of Vk minus T pi Vk. And from here, you see that the conditional expectation of this term would be exactly the same as this other term, conditional expectation. So this term, which is epsilon k, I define as epsilon k, is acting like a noise. It's a zero mean noise. So if I do compute epsilon k with proper conditioning, that would be 0. So what does it mean? This means that this empirical version of value iteration, the way I write it here, consists of two parts. One part is exactly the same as value iteration. So that's a kind of like the deterministic part. There's a stochastic part, which is the noise that coming from here, which would be the difference between the effect of a Bellman operator and the empirical Bellman operator. Is this clear? So, I mean, we don't want to run this exactly this way because of that noise term, because that noise term can be large, even though it is zero mean. So we somehow need to average out the noise and cancel out. We can do by taking, like if we have different random samples from the next state, we can construct different T hat pi of Vk, and then make the noise gradually go into 0. Or we can define a stochastic approximation procedure. And I'm going to talk about that stochastic approximation procedure to see how it works. So this is for policy evaluation. So we have a policy as input. We initialize V1, maybe equal to 0 everywhere as an example. And then we do it for many iterations, for iteration k equal to 1 to infinity. And what do we do? For each of the states, each of state x, I compute or draw the action from the policy, pi, and then get x prime of x, capital X prime of x. So that's a random variable from P, and we get R of x from distribution R, and then define the this Bellman empirical Bellman operator being applied to VK at state X, which is the same state that we had, as the reward plus gamma times VK. And then suppose I do all these computations for all state X's. And then after collecting all those values and storing them, I do a stochastic approximation update, which would be V of k plus 1 would be 1 minus alpha k times Vk plus alpha k times T hat pi of Vk. So this is like, this is synchronous updates. Like I update all the states synchronously at the same time. But it uses these empirical estimates in order to compute a better estimate Vk plus 1. So this is, I call it temporal difference learnings, the synchronous version of it. I haven't kind of explained why it's temporal difference, but probably becomes gradually more clear. Let's see if there was a question, I think. Yes, so the question is that, the alpha k here is trying to dampen the noise from epsilon k. That's right, so it's exactly doing that. So for this to work, we also need to alpha k to have a schedule similar to schedule that we had seen before. So it should gradually go to 0, but not too slow or not too fast. But here, okay, so the idea is that we do not need to actually update all the states at the same time. We can update only one state at any time and then keep the rest the same as before. So the procedure would be something like this. And then this is temporal difference learning algorithm. And hopefully this is a bit more clear the way I write it here. So it's very similar to previous case. So initialize value function. I initialize x1 from some distribution. So I assume this is a continual or continuing task. So I start from 1 point and go for infinity. And for each step t equal to 1 to infinity, I choose an action according to the policy, and then take an action, observe xt plus 1, the next state, according to transition distribution, transition kernel, which is conditional on xt80. So at state x, xt, I take action according to policy pi, go to xt plus 1. That's one step. And observe xt plus 1 and also the reward, rt. And then the idea here is that we just update using a stochastic approximation to update the value function for that particular state that we have seen. So how does it work? For state x equal to xt, the one that we just observed, v of t plus 1 of that state would be v of t plus alpha times this term, what is this term? This is rt plus gamma v t of xt plus 1. So this is the previous value of v evaluated at states xt plus 1 multiplied by a discount factor and added the reward. So this is basically the same as that effect of the empirical Bellman operator being applied to Vk. And then I subtract Vt of xt from it. So, and this whole thing is multiplied by the learning rate, alpha t, which is specialized for x of t, or is for x of t, and then add Vt to it, and that would be Vt plus 1. So that would be this is for the case that we have for the state that we just observed. For the other states, we don't change the value. We just copy the previous value here. So if x is different from xt, I just copy Vt to Vt plus 1. Okay, so I think, yeah. So this term this term is called, the green one, is called temporal difference error, which is basically saying how different the first part of it is from the second part. Okay, so I think in a few slides, I have a better description of it. So this update can be, maybe the comment here is that this update can be written in a simpler form. So it can be written perhaps in this simpler form, which is just v of xt would be equal to v of xt plus alpha plus whatever we had before. So here I didn't distinguish between the, I don't use the subscript t, and also I don't distinguish between those values that are updated or not updated, but these are the same. So here it just doesn't show the explicit dependence of value function on time index t. So that's the same formula. Okay, the term that we had inside that stochastic approximation update was RT plus gamma v of xt plus 1 minus v of xt. This is called temporal difference error, and it's usually shown by delta of t. So this can be seen as a noisy measure of how close we are to v of pi. So that's the idea, that's the error part. If this is close to 0, our value function would be close to v of pi. But if our v is very different from v of pi, this value would be large. Of course, there's a stochastic part of it because of stochasticity of the reward and stochasticity of the dynamics and even policy. So this value is never 0, but it just, even when v is v of pi, but it just fluctuates around it. But in expectation, it would be 0. To see it kind of more clearly, suppose we have a transition x, a, r, x prime, and a value function v. So I define this kind of expanded notation for TD error. So I just show the dependence more explicitly. So x, r, x prime, and v. So that would be reward gamma times v of x prime minus v. If I compute the conditional expectation of it, condition on state x, we have seen it in similar form that it would be essentially this part gives t pi of v evaluated at x, and this part is of course this one. So conditional expectation of TD error would be the difference between t pi v minus v at state x. And if you recall, we called this Boltzmann residual of value function at state x. And one other thing that was interesting about, say, Boltzmann residual was that if v was v pi, the Boltzmann residual would be 0. And this is easy to see, right? Because if v is v pi, then t pi v pi minus v pi is 0. This is the Boltzmann equation. And it is unique and everything. So TD error can be seen as a Boltzmann residual, but the noisy version of it. And here the TD, temporal difference learning algorithm, is just adding, at this step, is just adding the TD error, how far we are from the true value to the previous estimate. If we are kind of always positive, like the noise has a positive bias, it means that we should make it smaller, and vice versa. Okay, so we can do this process for action value function too. The process would be very similar. So instead of estimating v pi, we want to estimate q pi. Okay, so how do we do it? It would be very similar to before, except that, okay, so we want to evaluate pi. We need to evaluate an estimate of t pi of q, which is a function of state and action. Suppose that at time t, I choose x pi xt at according to some distribution mu. So I choose state and action randomly, and then x prime t would be from the dynamics and reward from the reward distribution. So as usual. So when we want to update this, we update it like this. For x q of t plus 1 would become q of t plus alpha learning rate times this quantity, which is the reward, plus gamma times qt, q of t evaluated at x prime of t with the action of policy that is selected by policy at x prime. So it would be pi of x prime t. So this is the case that the action is, the policy is deterministic. So I write it as a function minus the qt at xt at. So you see that this is very similar to the previous case that we had here, with the difference that instead of v of state, I have q at state. And I don't update qt plus 1 for states that are not observed. And very similar to before, the conditional expectation of RT plus gamma qt at next state is going to be t pi q x and a. So this is kind of a noisy version of the effect of Bellman operator applied to q. Okay, so one interesting observation. Okay, so here when I chose xt and at, I chose it from distribution mu. But this distribution mu does not have anything to do with the policy. It can be any arbitrary distribution. And if we look at this formula, we see that the only place that the policy appears is this point. In the choice of action, this policy may not appear. The action can actually be selected by some policy which is different from policy pi. And this is kind of making sense if we go back to the definition of action value function, because action value function was saying that at the first time step, I choose action A, and then afterwards, from second time step onward, I follow policy pi. So the first action is not selected by policy pi. So in order to have such an estimate, I don't need to choose AT according to policy pi. I can actually choose another policy, say policy pi b, and follow that policy pi b, and generate actions according to that policy, and have this sequence, and then, but still evaluate the action value function for policy pi. Is this clear? Oh, so there's a question, I guess. Right, yes, so exactly, that's a point. It's of policy method. So when pi b is equal to pi, then we are in the unpolicy, it's called unpolicy sampling scenario, in which the agent is evaluating the same policy as it is following. So it is choosing action according to pi, and evaluating the same value function pi. But it is possible, as I showed, that pi b and pi would be different. The agent still trying to evaluate pi. So we want to estimate, say, q of pi, but then the data is generated according to some other policy, pi b, which is different. In this case, it's called off-policy sampling, as mentioned in comments. So we have on policy and off policy. Sometimes, I guess, people just say this algorithm is on policy or off policy, which means that that algorithm works with off policy data. Like this, the algorithm I described for estimating the Q function is an off policy because it can work with data that is collected in an off-policy manner. Okay, so I think it's better if I continue. I mean, if you have to leave, that's okay. I will put the video, upload the video soon, but I want to finish it so that you can do the homework. Okay, so I talked about policy evaluation. I described Monte Carlo. I described a temporal difference learning, TD method, for policy evaluation. We can do both of them for control. So the general idea is for Monte Carlo is to do some version of policy iteration. So if we run many rollouts from each of the state action pairs, so we estimate Q pi hat that is converging, say, to Q pi. If I have a very good estimate of Q pi, I can just do policy improvements. So I have a Q pi hat of t that converges to Q pi by the Monte Carlo estimation, for example. And if we wait an infinite amount of time, if the, let's say, stochastic approximation, the learning rates are set appropriately, this Q hat of infinity would be the same as Q of pi. So if I choose pi prime as the greedy policy with respect to this estimate, which is accurate, then I already found a new policy, greedy policy, which because of policy improvement theorem would be at least as good as the previous policy. And because of the policy iteration algorithm and the guarantee that we had, we gradually improve the policy up until we get to the optimal value function and optimal policy. So this procedure can be described by kind of this sequence of evaluation and improvement. So we start from pi 0, we evaluate that pi 0, we do an improvement to get pi 1, do evaluation, improvement, and so on and so forth. But here, this procedure that I described is not feasible because we can't wait until infinity before get a good estimate of the value function of a policy. So I think, so we do not need actually to do it. It turns out that we can show that we do not actually need to have a very accurate estimate of Q, say pi k, before performing the policy improvement. It is enough to have some approximate estimation of it, and under some conditions, then doing policy improvements based on this approximate estimation is going to be still leading a better policy. So sometimes this idea is called optimistic policy iteration. So let me show you how it can be done for Monte Carlo, but for control. So I use the version, initial state version. Here I start from some policy pi 1, initialize Q1. Okay, so for each iteration K, for all states action pairs, I initialize X1 equal to X, A1 equal to A, generate an episode from X1 by choosing A1 and then following pi K to obtain a sequence of, basically we have a rollout here. And then I compute just the return at the first time step. So this is initial state version. So I only use it for the initial state. And then update the policy, update the value function after computing this return for all state action pairs. I update it for iteration k plus 1 equal to 1 minus alpha k learning rate at that state that is selected times, so I guess I should be more careful here. So this x1 refers to one of these x1. So I have a kind of loop there. So I think I should, yeah, I guess this is right. Yeah, this is still within the same group, so that's fine. plus alpha k of that state and action pair that was selected times the return that I get from that point. So I update that value function. I finish this loop, which finishes this update for all states and action pairs. And then I do policy improvements. So this is Monte Carlo estimation for control. So we do policy improvement. And if we do this process, it can be shown that, so this is by Tsitsiklis. I think 2002. So the sequence that is generated, sequence of action value functions by this algorithm with proper choice of learning rate converges to Q star. So that's kind of interesting because even though we haven't actually evaluated Q pi k exactly, I just use one rollout, even with that, this process converges. So let's see if there is a question. Right, I mean, you feel free to leave. I prefer to finish it now because it's difficult to find another time for me to kind of have a class. But it will be recorded and you can watch it. And also, I wanted to do it. I can't do it for office hour this week because I will be away. So feel free to leave. Okay, so here, I think we are almost done. So this is this result for Monte Carlo control for initial state version of it. The problem, if you want to do first visit version or every visit version that I described briefly before, then the theory is not as clear as for the initial state case. It is not necessary, that process does not necessarily converge, and it's believed that it converges, but it hasn't been proven as far as I know since 2002. I mean, it's almost like 20 years, but nobody proved it yet. So that might be an interesting problem for project, but I don't know how easy or difficult it is. Okay, so that's Monte Carlo. So the other one is that, okay, so temporal difference learning, but for control. And I'm going to talk about Q learning algorithm, which we had seen before in the first lecture. So here the idea is similar. We can use a TD-like method for the problem of control. So the idea is that let's consider Q function. Let's X prime be selected according to some X and A, or P conditional X and A, and the reward is the same. And then they define the reward function as y equal to reward plus gamma times max of A prime of Q of X and A prime. So that should be like this. So if we do this, then we compute the conditional expectation of that. We get that it would be R of X and A plus gamma times this integral, which is essentially the integral that we had seen in the Bellman operator for Q, Bellman optimality operator for Q. So that would be T star Q evaluated X and A. So this basically shows that similar to the policy evaluation case, Y is an unbiased noisy version of T star of Q evaluated X and A. And then we can define the empirical Bellman optimality operator as similar to the previous case, T hat star of Q, which is R plus gamma max of Q. And then we can use the stochastic approximation to update the estimate of Q, R estimate of Q star. So this is going to be a procedure like this, that for the state that we observe, like XT and action and AT, state action pair that we observe. So QT plus 1 at XT AT would be 1 minus learning rate times Q of T plus learning rate times RT plus gamma max as before. So this is for the observed one, and for the unobserved one, we just copy paste the value. So that would be the Q-learning algorithm, this update rule, this stochastic approximation procedure, and it would look like this. It would be similar to before. So I have choose some x1, select action from some policy pi, and take action AT, observe action xt plus 1, and reward, and then update the Q function the way that I explained. Okay, so I think that's it. Okay, so I think I have one question now. And the question is that, what is the policy that the Q-learning algorithm is evaluating? Like, we can think of Q-learning as, if we compare it with, where was it? Here. TD learning for action value function. So here we wanted to evaluate policy pi, and the update rule that we had is actually, you see, it's very similar to Q learning, except that this term is a bit different. So in Q learning, we have max A prime of QT, but here we have pi instead of that maximization. So what is the policy that's being evaluated here? Let's see if there seems to be some action. Okay, so the greedy policy, or, okay, so one answer is the greedy policy, the other answer is pi star. So pi star was the optimal policy, which is not true. But to see it's, okay, so maybe but the other answer, the greedy policy, is correct. Let's try to, okay, I guess I should. Okay, let me try to see it more clearly. So what we have is, so that specific term, I just ignore x prime and a prime. So this is equivalent. Okay, maybe I use subscript t to emphasize its t dependence. This is equivalent of t, q of t, x prime, and arg max of a prime, q of t, evaluated x prime and a prime. Okay, so here you see, instead of, I basically bring this maximizer inside, so I get this argmax there. But what is this argmax? This argmax is computing the greedy policy with respect to qt at state x prime. So that would be the same. So greedy policy at state x prime of qt. So the policy that Q-learning is evaluating implicitly is the greedy policy of qt. So this is interesting because qt is changing as we learn. So the greedy policy also changes. So the policy that the Q-learning is evaluating is also changing. It's always the greedy policy, but with respect to the most recent one. So that's, I guess that's one point. And based on this, is Q-learning an off-policy algorithm or on-policy algorithm? Okay, perfect. So it's off-policy algorithm because the behavior policy selected here, choosing here, it's pi, which might be the same, might be a different policy from greedy policy. In practice, people often use a policy that is very related to greedy policy, but in order to greedy policy of the current queue, but they use, but in order to kind of have some exploration, they use epsilon greedy policy. So in practice, maybe we use it as, say, we choose action this way. So this adds some exploration to it. And yeah, so I guess, but it is not necessary, like this is not a part of the Q-learning algorithm. So I think I am done for today. So what is left to be talked about in this chapter is an algorithm called SARSA, which is very similar, but with a slight variation. And also trying to prove some convergence results for Q-learning. So I try to maybe kind of record it next session that we have. So basically we'll have some results on convergence of stochastic approximation algorithms and use that in order to prove that Q-learning algorithm converges. And yeah, so okay, so another thing that I want to mention is that here in many of these algorithms, notice that we used the exact representation of Q. Like we say that Q of that particular state is going to be updated in this way. If the number of states is finite, we can do it. We can store it on computer, but if the number of states is infinite, we cannot do it this simply. We need to do some kind of approximation. And if we do approximation, we use function approximation, then similar ideas would work, but sometimes we need to do some modifications. And I think my plan for the next session after probably finishing that stochastic approximation part is go to kind of RL algorithms with function approximation. RL algorithms that are estimating the value function, so value-based methods. And then later in the course, I talk about policy gradient methods. So yes, that's the plan. If there is any question, please ask. Okay, so we have. Okay, so so there's a confusion about the behavior policy. Let me. So I imagine this is the slide that you're referring to. Right. Okay, so here, the idea is that in order to update the action value function, we need to, well, essentially compute or update the value for action value function at state X and action A. And when we want to do the evaluation, the computation that we need to do is add reward to Q at the next state and with the action that is evaluated or the action that is selected by policy pi. But this action, the way this action is selected is not necessarily the same as, is not selected necessarily by this policy pi. It can be selected by any other action. So essentially for any action that we have here, no matter how it is selected, we can define the action value function and have an update similar to this one. So here the idea about the behavior policy is that I could choose, like when I get at state xt, I could choose action at equal to pi b of xt, and then do this update and have, and this pi b would be, can be different from Where did I go? Okay, so that's not a very efficient way of. Okay, Q learning. No, I went before Q learning. Okay, here. So pi b and the pi that I want to evaluate can be different, because the only role of behavior policy is to choose this action AT to be used at this step. I don't know if this is more clear at all, or if you want to kind of expand on your question, or where the point of confusion is.
So it's clear. I'm just wondering, so depending on the properties of the behavior policy, the estimation error is going to be different, right? So I guess, can we say some behavior policies will converge faster than others? And
right, yes, so exact. So that's a good point. Yes, that's true. If not all behavior policies are the same, some behavior policies might be helpful for estimating a good action value function for uniformly for all state and actions. Some of them might be very bad. Just give you an example of extreme example of a bad policy. Suppose the behavior policy always chooses for all action, always chooses action for all states, always choose action 1, A1. So in that case, we never have any action 2 selected, which means that when I want to update here, I never update X and A2 for in any of the states. So it means that my estimate of action value function for any action other than action A1 would be very bad. It would never be updated. But even more than that, I mean, that's a kind of extreme example. But if another situation is that some behavior policy might help us explore the environment better, go to all regions of the state space, but some of them might confine us to some specific region of the state space. So maybe if I just show you, so if this is kind of state space, some agents following policy pi 1, pi b1, maybe I will show it. Maybe it just stays around here. It never goes in the upper region of the state. But another one, maybe I show with orange, pi b2, starts from here, but kind of goes everywhere. So this orange one, pi b2, seems to be more exploratory and allows us to have data collected from everywhere. So, I mean, roughly speaking, this is not precise, but pi b2 is a better behavior policy.
So if it so happened that the optimal policy looked more like pi b1, then using the optimal policy as the behavior policy isn't necessarily always good for Q learning. Can we say that?
Using optimal policy, you mean optimal policy be like pi b2 or b1? B1, right?
Yeah.
Yes, I guess that's a valid point. Like, if the optimal policy is like b1, and we always start from this region, so we never have a good estimate of the action value for state like here, because we never have samples from there. So if it turns out that the agent happens to start from this point at the top, it doesn't know what to do, because it essentially its QT does not have a good accuracy in those regions. And actually you will see, so yeah, I guess that's a good point. And you see that the condition for convergence of Q learning is that all state and action pairs should be selected infinite times. So, which means that we have to go everywhere and do it many, many times, like infinite times, asymptotically. So if one of the policies does not lead to regions of the state space, means that those states are not selected infinite times, which means that the QT that we get would not converge to Q star.
So one question: if the behavior policy gets over all space, so it just goes over all states infinitely, then Q will converge to Q pi for any temporal difference algorithm. So
you're talking about.
I'm not talking about
okay.
Q learning. I'm just talking about a temporal difference algorithm,
right.
Which the behavior policy is different.
Okay, so let's see if behavior policy is different.
But it also goes infinite times to every state.
Yes, that should be okay. Like if you have a Q representation for it, you can, like what I have on this slide, if your behavior policy go everywhere. So the behavior policy essentially only determines this, essentially affects the first part of it, like XTAT. So you're saying that it goes to everywhere, so it will be infinitely selected. The evaluation part only comes in this choice of pi, so it doesn't matter. Yes, so you can follow another policy. If it explores enough, goes everywhere, then QT that you obtain here would converge to Q pi.
So the proof that temporal difference algorithm for same policy works, it must be pretty straightforward. But the proof for Q learning or this scenario, I don't think that the proof will be so much different. It must be much more complicated, right?
The proof, okay, so for all of them, no, actually all of them are, depends, the easiness or difficulty of the proof depends on what kind of intermediate theorem you use. Like if we use the result in stochastic approximation theory, then using that result, as you will see, proving that these algorithms work basically requires us to know that show that the Bellman operator is contraction. And we know that it is contraction for T pi or T star. And some other condition of the level of the noise, which would be the same for all cases. So I think all of them would be the same, but they have a condition. So I guess the trick is the statement of those theorems would say that assuming that we visited all state action pairs infinite times, but they don't say that if you choose that pi b, that condition is satisfied or not. So that would be part of assumption. Like if we visit infinite often, then all of them converge, and the proof for T pi or T star, Q learning or TD would be the same for the discrete case. For finite action case, for continuous state, it's a bit different.
Yeah. Thank you.
Okay. Oh, sure. There seems to be a question.
I was just going to ask a follow-up. Is there a way to know what an optimal behavior policy looks like? Optimal in the sense that it converges the fastest compared to other behavior policies.
Yeah, that's a good question. I don't know the answer, and I'm not sure if we know the answer. Yeah, it is a bit complicated because we need to now, if you want to talk about rate of convergence, like how fast we converge, it's more than asymptotic convergence. So that would become a bit more technical. And then how to choose the policy that does that, that would be more complicated. So I guess the results I can say is, I guess maybe two things I can mention. One is that there are some results for rate of convergence of Q learning, rate of convergence. And those results are new, right? Not new, like there have been results around 2000, but still that wasn't necessarily optimal result. So still in 2020, people published papers on good papers on rate of convergence of Q-learning. And that wasn't even trying to find the best policy, behavior policy. So that's one answer. So I suspect we don't know what is the best policy is. There's another scenario that is called, we can think of it as if we want to find the Q star optimally, not necessarily using Q-learning, but in some way, while we are interacting with the environment, what can we do? So that's a bit different because then the update would not necessarily be like Q-learning or any of this stochastic approximation. For those methods, we know algorithms that have, at least asymptotically, they're optimal. And they are like similar to, I think someone mentioned in the chat, for bandit problems, we have UCB type of algorithms, upper confidence bound type of algorithm. We can have similar type of algorithm. Those algorithms are kind of principled way of doing selecting actions in the case that it's an immediate reward problem. We can translate those algorithms to RL setting, and we have an algorithm called upper confidence or reinforcement learning, UCRL. And I believe that algorithm is optimal asymptotically, but that wouldn't be like Q-learning. But that algorithm would say that gives you a policy that you should choose actions this way in order to balance exploration, exploitation in your MDP.
I see. Okay, thank you.
You're welcome. Yeah, but I guess that's a kind of interesting question. For what's the best behavior policy in order to collect as much data as possible, but also don't waste data in points that we don't care. I think that's a kind of we don't have a good answer for that.
Yeah, I guess that's how the curiosity in RL stuff came out.
Yeah, exactly. But those are heuristics.
Yeah. Okay, thanks a lot.
Okay, so any other question? I guess this was the longest lecture session so far. Hopefully it remains the maximum.